So what does that probability look like? Well, this figure's a little bit misleading because the x-axis is on the log scale. But if you just look at the heights, what's going on here is on the y-axis is the probability of drawing a particular digit. The blue line is associated with the digit 1. The green line is a digit 2, and so on. And this was generated by a simulation where I really did select random numbers from a distribution, and then I really did order them in the manner described in the previous slide, and put one in and then measure the probability of drawing it, a value with a number 1, or where the first digit is 1. Okay. And so if you think about this, the numbers, what's happened here, this is where 1, and this is 10, and this is 100, and so on. Well, as soon as I put a 1 in, the chance of drawing a card with a 1 in the front is 100%. When I put a 2 in, it's now 50%. When I put a 3 in, it's now 33%, and so on. But then as soon as I get to 10, it goes back up to a higher percentage again. And it stays there, 10, 11, 12, 13, 14, so on. And then as soon as I get to 20, it drops down a little bit. And so that's why it's climbing here, is through the 10s, and then it starts dropping again, sharply. Okay. And so the point here is that under this model, values where the first digit is 1 always are in the hat already by the time you get to the 2s. And the 2s are always there before you get to the 3s, and the 3s are always there before you get to the 4s, and so on. And so you end up with these peaks are led by the 1s, and the area under this curve, although remember this is a log plot, so the area is not quite right, represents the probability of drawing this. And so the probability does actually get higher. Okay. And there's a few different other models you can find if you read up on this, and I encourage you to. There's other ways to sort of think about the probability here, and there is actually a closed form expression for Benford's law as well. What are the limitations here? It's not always true, and one of the key situation in which it's applicable is the data set has to span many orders of magnitude. Right? It can't be values between. Think about it. If you have values between 50 and 90. And you select those randomly, well, you're not going to get any numbers with the first digit is 1. Okay, and similarly, if you do from 1 to 100, well, you have this effect a little bit, but not universally. So you want to span a lot of orders of magnitude. And so this is sort of illustrated by this plot here, is that the red areas represent the probability of selecting something where the first digit is 1, and the blue areas are where the first digit is 8. Okay, and so as long as you span enough orders of magnitude, you get much more area where the first digit is 1. Okay, but if you take a narrow case, well, and then the probability is more defined by the distribution itself, and there's not enough chance for this area under the curve under the digits 1 to get big. Okay, so fine. So I just want to introduce you to that law, mention that it can be used to detect fraud, and then connect the fraud plus chance of mistakes back to this original context we're in of trying to understand the weakness of statistical results, the perceived increasing weakness of statistical results.